So I have a rough plan today, which is I want to start by, which is the following. So I want to start by saying something about the gamma conjecture.
Is it rough? It's very rough.
I mean, it's like extremely rough.
Really tough. Really tough.
Tough? That's right. That's right. It's very yeah. That's what I mean. So I'm gonna start to say something about gamma conjecture. This is something I omitted to say earlier, and so I thank you for pointing this out. So I'll say something about this. Then I will recap the trick we did. So there's two aspects of this. The first is geometric, and the second is about these canonical coordinates. Like I've been telling you a lot about canonical coordinates, so I should at some point we should really be talking about canonical coordinates. Then I will recap this log local correspondence and I will ask the audience the question: what is the HMS version of this? Which I know nothing about, but maybe some of you do. Then, based on popular request, I will bombard you with identities of J functions. So that will be a very formulaic and tough part of the talk. And then at the end, if there's still time, then I will say something about numerical constructions. So gamma conjecture. So remember, so if we have some x and x check, which are Clavial and mirror pairs. So it could be local Clavials, but maybe also you want to think about compact ones as well. And if you have an element in the core of x, E, that is mirror to an element of the Fukaya category, x check, some parameter t. So E is mirror to some L, and if they correspond to some tropical cycle in the SYZ vibration. So whatever that means, I'm being very deliberately vague. So this is right there. Here you have some sheaf, and then you want to be looking at its support, and then you want to tropicalize this. I made some comments about how that might look like. And here you want to look at a S1 to the n-k vibration. And you want to think of them as being inside respective Hodge groups the way I described this. So and then the correct expectation between the relationship of the two integrals. So on this side we want to do a pure integral, and on this side we want to take a term of the J function. So the expected relationship. So this is the conjecture relationship in this setup, which maybe goes back to Bosono. Then there's Iritani et al. I'm not quite sure about the history here, but then the relationship would be that the period integral over Lt, omega t, should be equal to the component of the J function that you get by doing the following. me explain this. So here we have the same period integral that we've always had. And then on the left-hand side, we take the j function, and then we pair it with some class, which I will introduce right now. And then there's some 2 pi I to some power. That's the thing that's been showing up a lot. That comes from, if this one is fiber, then S1 to the n minus k, then this period integral will pick up a 2 pi I to the, 2 pi I to the n minus k. So let's just take care of this. And then here you cap with the Chern character v. This is Chern character. V and E are the same, yes. Many things are the same, including V and E. Yeah. Now, this is, if you remember yesterday I wrote the J function in like terms, and so you should think about this Chern character kind of picks out different terms. Yeah. And then you just take the degree. But we also have this gamma class, which I will tell you what it is now. So remember, so then I'm going to define it in 2 ways. So if you take the tangent bundle of x, and then you can write its Chern class as a product of its Chern roots. And then the gamma class of x, and this is an x, of course, x is also equal to y, and it will just be, you just replace these products by gamma of, by the product of the gamma of the terms where gamma is the gamma class, so gamma 1 plus x is defined as d equal from 0 to infinity e minus t to dx d t divided by t. So this expression is we saw this earlier, right? So we write this as e to the log tx. So this is equal to 1 plus log tx plus log t squared x squared divided by 2 plus etc. You think about these being homology classes, so that defines a homology class. It will be a finite sum because eventually you're gonna be 0, and then you take the and then you just take the integral, the log integral of this expression. Sorry? That's not the formula for x. That's just the formula for gamma of 1 plus some Chern class. I'm going to give you now the formula for gamma of x. Oh, this is a usual gamma function, yes. Yeah, so this is the same formula as this. So yeah. So this is the usual gamma function. Do you agree?
Yeah, not the gamma of x.
That's right. So okay, you're absolutely right. Usually, I would define gamma of x, but since in this particular formulation, I have gamma of 1 plus something, I just write out gamma of 1 plus. Yeah, it's just just notation. I'm just trying to be efficient. And then if you plug this in here, then you will get that the gamma class of x is, and so this is homework, minus bits of gamma c1 x, so c1 of the tangent plus the sum k equals to 2 to infinity minus 1 to k zeta k, so this is the Riemann zeta function, k minus 1 factorial, return character of k, of the type function of the orders. Luckily didn't run out of space, and little gamma is the Euler something, Euler, what was it called, Euler and the constant of Euler m something constant, and it's equal to the following. It's equal to the limit, or it's defined to be the limit as n goes to infinity of the harmonic sum 1 plus 1 half plus plus 1 over n minus log of n. So it's a difference between the harmonic sum and log of n as n goes to infinity. That one, yeah, thank you. Euler, Ma, Ma. I know, yeah. So there's no space anyways. Yeah, thank you. All right. So this is the, yeah. So the gamma conjecture tells us that actually when we do these identifications that I hinted at yesterday, the correct way to do it on the left-hand side is we have these this kind of weighting that happens, right? Remember, this is a function, a cohomology valued function, and then we weight it in different ways. Now, so there are two versions. There are two versions of the conjecture. So this is the full version, and then the well, I mean, another way. Sorry, they're like there's also an asymptotic version, which is identified for t very small. Okay, very small. Yeah. So this is an asymptotic. Identify the asymptotics. So this would mean that, like in this expression, I'm going to look at the terms that do not depend on t, and I want to look at the what these terms are, and I want to compare it with the same on the other hand. So this is essentially, so it tells us the constant coefficients of the integral of Lt omega of t. Right? Maybe I'll give you an example in a second. And so this asymptotic version was proven in several cases. So the first case is, well, sorry, I'm not sure about the entire literature, but certainly there's a paper. Where I have my notes of it random. So there's a paper by Michel about where are the G? Sorry. Well, I know, but first I want to just say the toric case. So this is for the toric caveat, right? And tropical cycle, right? Tropical 1 cycle, or tropical 1 cycle, right? So you did this?
Yeah, for this one, it's not only asymptotic.
So this is all, everything? That's right, yeah, sorry. So this is, yeah. So there's two versions. This one is the full version. Yeah. Which is in the setting of toric not toric, any dimension? Or?
Canonical model.
No, yeah, sorry, or maybe canonical model, okay. Okay, sorry, yeah. So this would be k of x, k of y, for y final. Toric final, is that right? Fantastic. It's a fantastic paper where this is done, where you have a tropical cycle here that lifts to some Lagrangian, which is 500 s for k minus 1, and that corresponds to the curve. A very nice paper, recommend it. So this is the full version, and then for the asymptotic version, we have papers by asymptotic. We have a paper by also Michel and and Yang Zhu. So this is for the tensor surfaces. And then there's also another paper by Aleshkin and Michel, which is for toric funnel. There may be some other papers. I think, yeah. And so those would be my asymptotic version. And here, this is in the pencil case, and so this is in the bottom case. But there's also
I think the original one might be the AGIS.
AGIS?
Oh,
absolutely. And so then there's Abu Zaid, Ganatra, Yutani, Sheridan. So I think they do it for K3 and Clavia 3 hypersurfaces. Is that correct? Or battery coercive.
Battery.
Battery coercive. And maybe I can make a comment, since we've seen this picture several times. So in their paper, if we look at K3 case, we have this tetrahedron, whatever that is, that we've seen several times. It has these focus singularities, and then I think what they consider is, so they consider the period integral corresponding to the positive real locus. This is positive real locus. And then they find that asymptotically this will be is it 20 -24 zeta 2, or is it minus 24 zeta, yeah, plus or t epsilon. This is minus 24, right? And then what happens is this minus 24 is the difference between the polytope volume and like tropical approximations. So if you took the positive real locus and if you look at the monodromy of it, as you go around zero, there's a the first term is going to be the volume of the polytope, and as you go around, you're kind of missing little bits of zeta 2 for each of these singularities, the minus zeta 2, and that's where you get this expression. Yeah. No comments about this? Yeah, fantastic. And then maybe this is useful to point out that in our paper we also get these ZR2 terms that come up exactly the same way. We will also have a number of focus singularities, and then if you just apply the argument, you find that our constant terms are exactly the number minus the number of focus singularity times 7 by the exact same amount. Right, fantastic. So that's the ground projection. Questions, comments? Anything more that should be said? Okay, great. So now I want to just briefly recap the trick. And then maybe I can also tell you then how we get the ZR2 terms. Oh, so if you remember what was written here, you could see the ZR2 terms. So anyways, you could have pretty great. Recap the trick. So the trick is as follows. So if you take, I'm just showing it for KP2. So we have this map from KP2 to C that was integral. So this map, if it's just toric, this is a map from. So this is total space of 4 minus 3 and P2. And so such a map corresponds to a section of all of 3. So S in H0 of all 3 by classical algebraic geometry. Now, if this section is chosen to be X, Y, Z, then that map is this is smoothing of toric components of P2 of K2. We really have this. We have this polytope. This is a polytope of P2, and then we'll have these local equations, and so we have this like t direction, or this smoothing direction, which I'm going to call t. So t is always going to be this smoothing direction, and then locally around here we'll have x, y, z equals t. Then locally around the point here we'll have z1 times z2 equals t. So there could be always some kappa, which are ignoring now. There could be some powers. And then you're smoothing this out. So it's a smoothing where you start with these components and you smooth it out to C star squared. Yeah. So that's the smoothing. So this is the smoothing that shows up in KQ and various work. Now we're gonna so one way to view the construction that I described yesterday is we're gonna change this section to be something a bit more something a bit tougher. Which we're gonna change it to S equal X, Y, Z plus T times F, where F is a homogeneous degree polynomial. And then we've seen that the effect of this is we're replacing this picture. So here, right, so what I've drawn, so the facets of the 5/0. And when we do this smoothing, now the 5/0, so for the, let's call this S0, so for S, the 5/0 is going to be so P2 union along E of the total space of O minus 3 restricted to. You can compute what this is, it doesn't matter. Yeah? So it's going to look very different from it. The way it's going to look is you have this elliptic curve here, which should look like this. Or it doesn't matter what it looks like. And then you have the line bundle over it. Do you see this color? If I use this color, is that okay? Is that okay to see? This is, I know I'm a bit colorblind, and then that means that there are some colors I see and some colors I don't. But okay, fantastic. So this is going to be the central fiber. You're going to have the P2, and along this elliptic curve, you're going to have this line bundle P2. And then one way to think about this is, so equivalently at the surface level. So that's another way to describe what we did. And then yet another way, if you just look at the, looking at the so we're going to think about, I'm going to call this S. So generic fiber of S. What happened is, so before we had this toric divisor, and then we're really doing this nodal trade that we saw in the discussion section, where we replace this point by a S1. So all of these 3 points by an S1. We saw that this was necessary if we wanted to get an SYZ vibration, and then we will have colors. Something like this. But because we took a point and made it an S1, it's a price to pay. So before, where we had this torus vibration over the interior, that would shrink to an S1 in the boundary or a point of the boundary. Now we introduced 3 singular fibers, where this is, these are the single fibers, which now create these, create multiple surfaces. Good. So in particular, that means this implies that the P2 minus E has a lot more disks, has a lot of Maslach index 0 disks, because they come out, and then when they meet, they can combine to scatter around. They may combine. So may combine and scatter. Now, so this is the canonical singularity side. On the other side, what this corresponded to was the following. So on the this is the I'm just going to call it A side, and on the B side, what we did effectively, what we just did is we introduced we had this U. Remember, U was the mirror to the general fiber. Mirror to U, and then so we replaced U by we added these 3 copies of C. And when we're thinking about this, there are several ways of thinking about this. One is before the U was a vibration of affine elliptic curves where you were missing some points, and there would still be like some kind of 3 singular fibers. And then by adding these, we just filled them out. Right? These are. And so then it becomes so C is an elliptic vibration, proper elliptic vibration. And then the way this showed up in case talk is that we had this picture that we had this weighted Q2 pushing out by mu3, and then we had this f equals 0. This was f equals 0, and then we blow up these points, which means we are introducing. We're closing up this elliptic curve, and then it becomes a actually compact vibration. So we blow up the base locus of pencil, basically of the pencil. So we have this pencil TF, in this case T x plus y plus 1 over xy equals 1, and then this has a base locus which we so that's and then So this what this trick tells us is that we can replace Kp2 by P2E, and on the other side this corresponds to replacing this vibration by just this, replacing Z, which is UV equals T1 plus x plus y plus 1 over xy. We replace it by T1 plus x plus y plus 1 over xy equals 1. So I'm writing it slightly differently, but that's fine. Is that clear? Yeah. So at this point, this is only motivated by mirror symmetry considerations. And now I'm going to tell you how to motivate this using categorical statements. Any questions? We also have this correspondence between Lagrange's S3 here and Lefschetz signals. And this here. Let me make comments about how this works at the categorical level. So we're now talking about this part. So there's work by Seidel that shows that the DB code. So here Y is. I don't remember what the exact setup is. Maybe Y is del pezzo. Maybe D is mu antiharmonic. I don't know if you have any questions about it. So then he proves that dB curve of the canonical bundle well, has like a fully whatever immersion or whatever the correct segment is in the higher category of Z, and where Z is the, let me just write it here for future safekeeping. So we have K, Y, comma D, and then here we have Z, which is Z is UB equals to D. I wrote it up in a specific way. Or I just wrote UB equals F. Very specific. But this should be thought of if you read very clear and Boyer's paper inside the total space of all U plus L restricted to U, where L is O minus O of D. So total space of U plus all of running out of, I'll just put L. L, where L is, so we did this, L is a line bundle after the block. L restricted to U, and L was this, in this particular case should be K minus KY minus some of the EIs, where the EIs are the exceptional on the low side, exceptional curves. Remember, we obtained this elliptic vibration by blowing up, obtained by blow up of base focus, which led to these curves EI. Now, yeah.
Symmetry is expressed of L restricted to U by D3.
Oh, fantastic. Fantastic. Great. So, tricky. So, total space of, well, inside, total space of, yeah,
That's like C2
times U. Fantastic. Oh, that's awesome. That helps. Thank you.
Special situation in a larger
Fantastic. Thanks. All right. Well, that was still true that this is U was this. U on the other side. So this should correspond to. So yeah, thanks for the comment. This here. This proper vibration. C. So this elliptic vibration. Fantastic. And now there's a process where you take so in this vibration you have some Left-shift spindles which look like this. So they start at one of the we have some singular fibers, and then that's where some vanishing cycle pinches, and these trace out some Lefschetz-Spindle. This Lefschetz-Spindle corresponds to an S3 out here. Now, when I say this, this correspondence works before you did the blow-up. Having done the blow-up, there's some modifications which I don't want to think about. So in that way, I'm being a bit vague. And then this correspondence works by showing that this process is called double suspension. By showing that double suspension preserves chiropractics. So at the bottom, I think that's a chiropractic of Lefschetz-Spindles. At the top, maybe this is just a chiropractic or graphic. And then it uses this fact that on this side we have this equivalence to prove this statement. Yes?
So, what if I consider the compactor as a positive, which is on the left-hand side, what it would be on the right?
Excellent question that I would like to ask you a bit. Anyone has a, so what you want to do is you want to replace this by compactly supported.
Compactor supported is
Yeah. Yeah. Excellent question. Can someone tell me how I should modify the statement?
Then I think the impact category would be like the one generator impact. Here is if you consider the whole coordinates, then the impact category should be locked.
So, sorry?
Yes, there it is.
Yeah.
Then if for capacitor points, the not generator.
Great. Does that somehow answer that?
But if you add this part of this correspondence of KY to the log pair, so now what would be on the log pair side on this side?
So you're talking about the categorical version of the log code.
Yeah, more or less.
And maybe the question will be, you can ask the question on the B side first.
Yeah.
Is there a correspondence between variations on the canonical bundle and that of down there?
So, I mean,
I
that's
think
it.
in toric cases, you can check it. Because the definitions are in toric. But in general,
Yeah, I mean, yeah, so that's really the question. I think that's really the question that I have no idea.
but then on the right hand side, that's the correspondence that Michel explained yesterday.
That's right, yeah, that you explained to me 10 years ago.
So it's actually due to very originally people Gross and Joyce. They have correspondence between the plungins and the sympathetic quotient by the S1 action
Yep.
and the plungins on the total space.
Okay. So that's about here. So to the sorry
Yeah,
here.
the Z. Yeah, you have S1 action on there.
Yep.
And then it's actually not difficult. There's correspondence between the plungin section on the sympathetic quotient. Z by S1 with the sympathetic quotient, and then the plungins in there will correspond to the plungins in mu inverse 0, contain mu inverse 0. You just take the pullback.
Yep. Lagrange's in. So So here we have an action, then we take the moment map, and then Lagrangian sections or heat Lagrangians in privilege of 0, and the last step was they was what to.
This is like a correspondence.
Oh, that's right. Then we're there. Yeah. Then we're here. Yeah. Fantastic. And so what you're saying is this is well understood, right?
Yeah. Well, just talking about the prime.
Lagrangians.
Not the prime.
Yeah. Okay. So then the first question is, what is there modification, or what's modification if I do this flow up, right? Where I maybe the setting you're thinking about, this map here is just from C star squared to C, right? Maybe? Is that correct? This elliptic vibration will be like x, y equals 2, I don't know, x plus y plus 1 by x, y.
Maybe up to some other, because the sympathetic quotient will be symmetric to the model, you see, it's not really.
Yeah.
Which is the base U that you
Yeah.
talked about, but up to a certain model.
Yeah. But what happens if we close up this, right? If we compactify the fibers? And we want to do it on both sides, right? So yeah, so that's something I'm yeah. So that's the first question. So for question 1, so correspondence of Lagrangians for U, the compactified one. So for U equals for fiberwise compactification when fiberwise compactification. That's the first question. I don't know. Maybe someone has some idea. Maybe someone can do this. Fantastic. Question 2 is of course sheaves, as you said, like correspondence for sheaves. Z versus U. I don't know. Maybe someone knows. Yeah. So that So really, I'm Conan asked some questions, and so I'm just stating these questions. That's why he doesn't need to be here because we asked the question. Yeah. So that's on this side. But then you can ask, what about the statements on the left-hand side? So on the left-hand side, we have also. Right, so what about DB core may be compactly supported, probably, and versus DB core of Y comma D. And here the first question is, what is this? What is this? So I don't think we know what sheaves are which have some tangency condition. So that's a big question mark. What about maybe wrap the category of KY versus wrap the category of YD or Y minus D? I think that's also a question mark. So yeah, there's a lot of I think it's really not clear. And it's really not trivial because the other question you could ask about symplectic homology, right? But then you immediately realize that you don't understand what's going on because you could ask the question about, well, what about symplectic homology of KY versus symplectic homology of YD? I mean, I write pairs, but by pairs sometimes I mean the complement. And I don't know when I mean which. But if you ask this question, that's a silly question because that one is 0. And that one's definitely not 0. Yeah. And also if you look at the definition of symplectic homology, so if you look at, so there's work by, I don't remember, but
Yeah. So, but if you do look at this, you look at the relative homology variable.
yeah,
So law.
yeah,
He
yeah.
has a comparison between
That's right, yeah. Yeah,
the
so,
variance of these two sides.
that's right, yeah. So in terms of local glomerulitin, gene is 0 local glomerulitin versus relative glomerulitin of Y, D. And here we really, so there's a paper by Fenron, so Fenron U and 1, U1, maybe U1.
I think you can take the open variable, the counting decimal.
Oh, yeah, that's right. There's also a statement for open invariants, absolutely.
And then on the right hand side, you take the relative invariance with some contact order. Then you can also have some comparison.
Yeah, so I think this is related to mirror map actually.
Yeah.
Yeah, so relative mirror map. And I'm planning on saying something about this as well. Plus some absolute, some GW of Y. Okay, so at the glomerulitin level, there are many correspondences, and I'll say something about this very shortly. Now, if you look at the definition of symplectic homology, and maybe you want to look at not just the definition, but like the way it's computed, you will find that for the computation of this one, so this is a paper by so Lisi and Diogo. So there's a Luis Diogo and maybe Lisi. They have a paper where they tell you how to compute this, and they will be using uses maximal tangency glomerulitin invariance in the differential, I think, in the differential. But on the other, but then the corresponding local invariants, local invariants show up in, I think, in the product maybe. I don't remember. They show up here somewhere as well, but they show up in the product, but it's anyway zeros. So this is done by reason. So there's something not clear.
That is 0, just because Michel actually use something like KY.
Oh, fantastic. Okay. Yeah.
And
And
remove some
how do you call this?
dividing.
So yes, so you remove a smooth divisor, I guess. Yeah. Okay, fantastic. And then okay, that's excellent. And then do you think there will be correspondence? Then okay, that's really useful information. So I'm looking. Yeah, maybe we can discuss this more. I'd be very curious to talk about this.
Also, I think the ODC is considering divisor content.
That's right. Yeah. That's right. So another thing I don't understand is there a difference, and what is the difference between pairs and complement? But just complement. Yeah. Well, yeah. But I think there are statements in maybe from my Dharma and friends where they define symplectic homology for pairs. Or maybe it's Sheridan and friends. I don't remember. But there's something. So I think there's a bit of a subtlety between. So there's this work where they show that quantum homology is a deformation of symplectic homology, and so there's that statement. There's also like a pair symplectic homology pair statement. So these are things I'm not. But anyways, but you're absolutely right. Here I should put this perfectly. And this is not the same D, so it's called this curly. Not everything is the same. Right. Yeah, so here there's something to be understood. Do you think you know how to prove that they're the same? discussion session. Fantastic. Good thing to do the discussion session. Great. Very good. So I think there are many, thank you for the questions and for the comments. I think there's a lot that can be said about these things that is still movable. Right. So Conan asked me to say a little bit about this, how these invariants are related. And I will say a little bit about this after the break. So I will tell you kind of the statement that I will make is that actually ky corresponds to y times a1 and then d times a1. But in fact, if you look at Feynman's work, there's actually modifications. A modification C Feynman, C U and 1. So Feynman U and U1. They don't consider this space, but something a little modified. But I'll say something just briefly about this, since to answer Connor's question. And then we will go to identities of J functions. Okay. So maybe now is a good time to stop within the limits of what I'm allowed to.